All right, welcome to Developing Breakout Models in Femap webinar. I'm Ryan Tatman, and this presentation is just going to go through a few things. First, I'm going to go over who SDA is, or what SDA is, and what we do. Then I'm going to define what a breakout is and when to use it. We're going to go through a couple examples, and then we're going to draw some conclusions. So SDA was founded in 1997, and our goal is to provide expert aerospace structural analysis. We specialize in composites and developing strong lightweight structures that are readily manufacturable. We provide anything from low-level support to advanced stress analysis. Our team consists of over a dozen mechanical and aerospace engineers, ranging from a bachelor's to a PhD. And we're located in Sterling, Virginia, just north of Dulles Airport in Washington, D.C. area. Some of the projects we've worked on, Aerosons, we've got the Orion Crew Module, we've got the Shadow M2, basically in atmosphere and out of atmosphere aerospace structures. We are a Siemens Value-Added Reseller, so we support Femap, NX, Fibersim, Solid Edge. We also support HyperSizer. So today we're going to spend the time looking into Femap. All right, so what is a breakout model? I've defined a breakout model as an analysis model created to represent a portion of a large structure in order to get more specific information. So it's pretty vague, broad, I guess. I've got a picture below that kind of points out an example of a breakout model. So you've got a large pressure plate, orthogrid pressure plate, and you've got a boss in there for maybe a fastener. If you've got a large model, you obviously can't mesh very high fidelity, so you're not really going to capture what's happening in that filled region I have blown up there to the right. So a breakout model might help you look in there, see what your stresses are, see if that fillet's going to be enough. Basically just give you more information. All right, when is it needed? So other than that example, a model is needed when a small design change requires analysis. So that can be a small portion of a large design that maybe needs to be iteratively designed. You don't want to run your large analysis model over and over and over again, so you create a breakout model, iterate that. You save a lot of time on the solution, computation time. Or when a feature is added to an existing part. So I'm going to run through an example later with a wing. So let's say avionics wants to put a pass-through through one of your ribs. You don't want to run the entire model with a new mesh in there. You might just want to do a breakout, something quick. And then I'm going to do another example later on that shows the second. It's just the examination of a localized stress riser. So maybe your giant model doesn't allow for the fidelity needed to see specific locations, and a breakout model might be helpful there. So this first example is going to be adding a pass-through to a wing rib. So we're going to move over to Femap now. So you have a wing model, and I've run an analysis on this already, so we have data, and we just want to add, let's say, a little circle to one of the ribs. So first we're going to isolate that rib, try to see it. And we'll just pick one, this one. So we want to create a group, call it something meaningful, breakout rib. And we're going to want to add elements. So I'm just going to add elements by property. Make sure I grab it. It looks like I have active view on, so I'm going to show full model. Go back. All right. So we're grabbing these elements, make sure we got the right ones, move them in. All right. So we're going to add related entities just to add all of the other things that this is going to need. And we're going to create a new modfem. Using the file merge, we're going to find our model. We don't want everything, we just want from the group. We're looking in there, and we're bringing in coordinate systems, nodes, elements, everything we're going to need. So we have our mesh in here. So we're doing a breakout, so we could just keep this mesh, right, and just adapt it. But we probably want to have a little more fidelity. So you can remesh. It usually is better to refine the mesh instead of remeshing. The way that this maps the loads is it tries to find a node as close to the original node as possible, and if it can't find it, it has to interpolate or do some of these other methods that I'll point out later. So you're better off refining the mesh so you keep your nodes in their original location and just add more elements, more nodes. So this mesh editing element refine does just that. It gives you a couple patterns, so you can turn one element into 9 or into 4. We're just going to do 4, area drag. So now we have 4 times the amount of elements. So that's going to be good enough for us. So now we need to add our pass-through. Just going to make a surface from the mesh, just something quick. Pick a square. This is arbitrary. Obviously, you'd have some more constraints with your designs. So we're just going to create a circle. First, we're going to define our work plane. So we have to define our work plane whenever we're working with the geometry 2D. So we're just going to create a circle, simple circle, just in the center of here. Oop, maybe not the center, slightly offset. All right, we'll do, yeah, that sounds good. So there's our circle. We're going to project it onto our surface, and might as well make a pretty mesh. So we'll just do some guide curves on there and join these weird broken edges that we got with that thing. All right. So we're going to mesh it just like anything else. Make sure we have a property. Probably want to map to mesh, something quick. Here you got to make sure that these line up. Because you're just editing a mesh, you're not going to have, your non-manifold add. It's going to be separate, so it's going to define itself. So you're going to use this mesh sizing just to try to get it close. It should be exact, right? So looks like we got maybe 10 in here. Nope. Oh, wrong way. Sorry about that. Can't get it right. All right, and we got 6 over here, and we're just going to clean that up. I accidentally clicked the wrong line, so something simple. Now we have free edges around here, so we're going to have to coincident node check just to get those out of there. So it looks like we got them all. And just to double check, we're going to do a free edge. And that's how you expect it. So we're fine. Just going to clean this up. Okay. So now we're going to apply our load. So we're going to go to Model, Load, Map Output from Model. This is going to let us grab essentially loads from other models. We want our wing model. You have to pick a group. We already have a group for this, the Breakout rib. Output set, we only have one analysis. Output vector. So you have a lot of options here. You can do basically anything that Nastran can output, you can apply. So you could do forces, just make sure that you ask for grid point forces when you do the analysis. We're going to do translations, displacements. Here you have an option of what to do if it can't find a node. So like what I was talking about earlier, if it tries to find nodes that are close to the original nodes, here it's going to interpolate. I've had best results with this, but you can try each one out. We're going to apply a nodal displacement. You want to make sure that this matches what you've grabbed. It will let you apply a force as a displacement, so make sure these match. All right, now we're doing target nodes, so we're just going to select the perimeter here. So now we have our load. So it's translated, you can see the full wing moved, so you see this entire section is moving. Now we need to add constraints so we can run it. Just arbitrary names. Nodal, you can use previous because you've just selected the other ones, so it'll match. We're only doing displacements, so pins is fine for us. And we'll just do a static analysis. Right, looks like it's not running. I'm going to try that again. There we go. So it's going to be quick. It's a very small model, very limited amount of loads, so it's something really quick. So there's our results. I guess they don't mean anything without a comparison, so let's look at what we had on the other one. So without the hole, we've got a very similar stress layout. I'm just showing von Mises. But you do see that this hole is affecting it. You've got a stressorizer here, which what do you expect? So looks like a good breakout. All right, so we're going to go back to PowerPoint here. All right, so I included one slide here. These slides are available through this GoToWebinar app, or I think they'll be on the website afterwards. I'll make sure they are. So we're going to run through another example. This is a local stressorizer example. So let's say you have a large orthogrid plate. I just modeled a small section here just for computation and modeling speed, so I could create the model. But you might model something like this. So you've got your orthogrid, and you just ignore these bosses with your interface, your bolts, and you might just throw an RBE in there with the C-bush. But obviously you need to know some more information later on, so you might use a breakout. So we're going to go in. Oh, sorry, I seem to have missed something. All right, one more slide. So there are some options that we've seen people use. They're online. But there's hex mesh the area of the model, and there's a couple other terms that I'll go through in Femap. Or you could pull nodal displacements and rotations from an analysis and create SPCDs, enforced displacements, on a solid mesh breakout. Or you could integrate a solid mesh into your full model and run the entire model. So we're just going to look into pros and cons of each of those. So moving back to Femap, I have them modeled here. So I wanted to have some controls to compare this to. So I have the control of the model as you'd run it if it was a large model. So you can see you have a 132, 133 KSI von Mises. In here, I just a simple TET mesh of the entire thing. I'm calling this the accurate model. And we've got 96 KSI. So it looks like this is giving us artificially high results, which is, I guess, what you'd expect. So this is no element doubling. So you've hex meshed your boss in here, and you've essentially just butt jointed with your plate elements. And just to show that, you can see plate elements just come right up to that solid cutoff. This is good. It gives you accurate stiffness, gives you accurate mass, but solid elements are not able to support moments at their nodes. So you have a hinge condition whenever you have a plate element butting up against a solid element. So this can give you an artificial load path, and if you're not fully constrained, it could give you excessive pivot ratios. So in this case, we are pretty well constrained. We've got a nice connection to this boss. So it's fairly accurate. You can see we've got 92 KSI compared to our solid model of 96 KSI. So a little low, but it looks decent. So in this application, might be a valid way to do it. But in the applications where you can't run it, or maybe you don't know if it will run, you might need to do something else. Basically, you want to solve this hinge condition here. So there are some solutions to that. This is element penetration. So you've got your rib elements that are going into your solid. So all of your nodes are coincident, and you're just moving these rib elements into your solid. This will run, right? You're not going to get excessive pivot ratios because you've solved your moment problem at the hinge here, but you've added material. So you've added stiffness, you've added mass, you've added strength. So you'd expect to see a lower stress, which is what we find, 82 KSI. And it did push our stress concentration farther out. So in this case, it wasn't as accurate for this case, but there are situations where you might want to do this. It's a very quick and easy way, and it doesn't add many nodes or elements, so computationally not very costly. Element skins is another option. It's very similar. You're just taking a skin around your solid and butting into it. Solves the same problems, has the same limitations, and you can see that it has similar results. So we got 82.5 KSI. So this is a solid breakout interface nodes is what I've called it. But basically you've taken a small section of your large model and you've meshed it, right? So it's a lot of elements, a lot of nodes, a lot of fidelity. But you've taken RBEs and you've taken them from your source nodes, so the nodes from your original model, and you've spidered them out. And you're going to apply enforced displacements, right? So you're basically contorting this section of the model as it was when you had just had plates. So this is going to be really, as with all enforced displacements, it's going to be really sensitive to stiffness. So we've added this giant boss in here. We've really increased the stiffness of this small section that we've cut out. So when we apply our displacements, we're going to get a really high force moving through our model, really high stress in our model. And it shows. We've got 234 KSI. So, I mean, that's really high. So you can see I took a border of 3 elements off on the out here. That's because these RBE elements tend to push high stress, artificial stress risers into your model just because they're so rigid, perfectly rigid actually. So I'm just going to show what this looks like if you didn't take those out. So you can see you've got these really high stress areas where these rigids connect, 467 KSI. So for this application, this did not work very well. The really high stresses really aren't giving you a good feel for what's going on in the situation. So this last option that I'm covering at least is a zipped in model. So here we've taken that same TET mesh that we have in the previous, but we've zipped it into our plate models. So this is our full model. We've just zipped it in there. And it doesn't necessarily have to be the full model, but you want to make sure you go out far enough to where the changes you're making to the stiffness are next to nothing, right? Small percentage. Then you're going to have accurate results. So in this case, I took it to the full thing. I didn't use enforced displacement. I just applied the original loads. And we got really good results. We've got 95.3 KSI compared to our 96.0. So this one worked very well for this situation. So I'm just going to walk you through how to do this, how to make this. So we've got our analysis model. This is your plate model, your giant full model. And we brought in our geometry. So what we're going to want to do first is we want to define where we want our breakout. So we're going to start with the work plane just so we can use our geometry in here. All right, and I'm just going to make a rectangle, and we're just going to pick. Got to get out of that mode. We're just going to pick a rectangle about this size. You're going to want to get as close to the original nodes as possible. So it doesn't mean it won't work if you're not close to these original nodes, but you're going to be more accurate the closer you can get to those nodes. So you're definitely not always going to have these perfectly straight lines that cut through all of your elements. So if you have to sacrifice and go a little farther away from some node, just try to get it close. The closer you are, the more accurate you're going to be, but it doesn't mean that it's going to be inaccurate if you're not close. So we need to split our solid here. So we're going to use solid slice. We're just going to slice with that curve, a long curve normal. It's a flat plate, so it's just a simple way to do it. We're going to grab our solid. We need to pick our curves. So we're going to slice these 4 curves coming up. We're just going to let that go. All right. So now we've got our solid, we've got our slice. I don't need this outer portion, so I'm just going to get it out of the way. All right. And the same is true with this plate mesh in the middle. All right. I'm going to mesh this solid, so I don't need these plate meshes anymore, so I'll just delete those. All right. So you want to keep your interfaces. It's just going to be easier as far as speed and everything not to have to redo these. So we'll keep them, we'll address them later. We're just going to delete this mesh. So you can see we've got our plate mesh and we've got our solid. So I'm just going to do something quick. You can do any type of solid mesh. You can even do plate meshes if you want to. But I'm just going to mesh the solid standard. All right. So we've got it, and now we need to connect it. So to connect it, I'm going to use this mesh connect rigid command. It's pretty handy. You're just going to collect your source nodes. So I'm just going to move over here. And we're just going to hide the solid elements just to make this easy. Click on our source nodes. And the source nodes is talking about the least number of nodes, right? So I have one node here that needs to go to multiple nodes in my solid. So these ones are going to be my source, and the solid nodes are going to be my target. Easy way to think of it. I don't want to grab my interface there, so I click OK. I want RBE2s. I'm just going to define all 6 affixed. User defined, so you can use automatic, but the automatic is going to reach out by a certain distance, right? So your distance of 1 inch in this case, you can change it. But that's going to start grabbing into my solid model, which is not what I want. I want it just to grab the outer here, just so I can get a full breakout in there. So I'm going to select the nodes, switch back to my solids here, and it's just easy. Use on surface just to grab those nodes. Just going to highlight to make sure I got them all. Looks good. Okay. You have some options in here. If you're selecting your nodes, you might not need these, but they're there if you need them. Preview target nodes, I don't need to preview them. I just selected them. So now you've got these. So you saw these in the previous example. These are RBE2s, but they're pretty good. They just reached out and they grabbed some of the nodes here, spidered them out. So a quick, easy way to do it. Now we're going to bring back our plates. We're going to just update this RBE that we have to manage our bolt there. We're just going to pick the surfaces on here too, just because it's easy. There we go, and there it is. So not too time consuming, right? Pretty simple to make, and it's accurate, right? So we're going to go back into our PowerPoint here. And here I just put some overviews. So this is our control plate just for reference. This is the full solid model for reference. So I've written down some of the pros and cons and limitations. We've got our no element doubling. So you got your accurate stiffness, your accurate mass, but there's no moment support at the junction. So it's not, it won't always work. It won't always run. You'll get excessive pivot ratios. You'll get some other things. It can be unconservative. So it's basically meaning that if there was going to be a moment resolved here, and because you don't have any way to resolve it, it's going to find a different load path. So it's going to go somewhere else, and you're going to get an artificially low stress at this location. But each situation is different. Your element penetration solves the moment at the junction, but at the cost of a heightened mass, and artificially stiff, artificially strong, and it's pretty widely unconservative. So at all these locations, you've got double stiffness, double mass, double strength, right? You've got a double material there. So that comes with its own boundaries. Element skins, very similar. I have a note in here, I have seen thinner skins used. So let's say you've got something that it won't run because you've got some excessive pivot ratios. So you put a skin on there, but you don't want to pull a full-size skin because you don't want all of these artificially stiff, artificially strong side effects. So you put a thinner skin. Definitely a viable option, but just so you know, as you bring those skins to zero, you're essentially back at your no element doubling. So you have the same limitations of there. So you really can find a balance in there maybe. But these options really are, if you want to have a permanent solution that's not very computationally demanding, some combination of these can work for you. And here you have your solid breakout interface nodes. So this can be great. It can be a really fast way to model something, but it's very sensitive to the stiffness of your breakout. So if you're really going to change the stiffness of the place you're interested in, this probably isn't the option for you. because you're enforcing displacements, and every time you enforce a displacement, if you increase your stiffness, you're going to push more force, you're going to push more stress into your model, and you're going to get these artificially high stresses if you increase your stiffness. And the opposite's true. Let's say instead of having this, I just bored a hole in there. I'm going to get a low stiffness, which is going to give me, sorry, the wording there is a bit confusing. If I have a low stiffness, I'm going to get a lower stress, right, because I'm pushing less force, less stress into the system. But if you have a situation where you're not really changing the stiffness much, you're really just looking in there, maybe there's a small fillet that you're interested in, this can be a fast, easy way to look in there and see what's going on. And then the zipped in, it's a very consistently accurate way. It definitely takes longer to do, right? It takes longer to model. It's definitely more computationally demanding. But you can get some very accurate and very good looking models from this. So in conclusion, the map output from model is a quick way to set up loads on a breakout. Couple things to look for. You want to try to keep your nodes in the original locations. Try to use mesh refine, not remesh. Remesh will work. It's just, again, you're trading for accuracy. So try to keep the breakout stiffness similar in the original model, or to the original model, if you're using enforced displacements. There's other options like using forces that I didn't get into this webinar, but you really just want to try to keep your breakout stiffness similar to your original model. And that doesn't mean you can't make fairly significant changes. It just means you might have to grow your breakout size larger and larger the more you're making changes. Dummy elements, they can be used for ballpark estimations, but they'll often give an accurate result. And it's just because you have double material properties in those locations. And the zipped-in breakout model will give the most consistently accurate results. Just another tip there, you want to grow your breakout model by at least 3 elements from the point of interest. And that's just going back into that RBE, kind of pushing these stress risers into your breakout model. You can never really trust the first 2 or 3 elements after your RBE connects there, because there are some weird rigid body rigid body element effects going on. All right, so that's it for the webinar. I just want to point you to some additional resources. Our very own Eric Gustafson wrote a book. So it's basically just an intro to Femap. You can find more information online at the website here, and it gives you some examples over here on the right. And contact. Looks like my contact information was not updated, but I'll be sure to update that on the slides that go up on the website, so you can contact me with any further questions. And I hope this was helpful. I think there are a few questions, so I'm going to look into those. All right, so I have a question on here. Sorry for the echo. I have a question on here asking what version of Femap. Yes, so a lot of the things I used in this demo are new in 11.3. So I'm using 11.3.1. So I think the person who asked said they're on 11.1. Updating will give you some of these newer things that honestly I think help me day to day.
Can you describe why you used an RBE2 instead of an RBE3 around the edge?
Yeah, so I used RBE2s because they're robust. RBE3s are good. They'll give less interactions, less stress risers. They're less likely to push those higher stresses into your model because they're less rigid. But an RBE2 is just more robust. If you can get an RBE3 to run, those can be great.
Ryan, if you're done, we can sign off.
All right, sounds good. Thanks for everyone who joined in.